So if an ELF file has our machine code at a particular predicted address, and if object files are represented by ELF files, then what will the addresses for A and B be in these cases where I separately compile A and B? The compiler, does that mean it picks a place for A and picks a place for B? And if it does, how does it know that we're eventually going to link these files together and make sure that it doesn't assign the same address to A and to B? Just to look at that, I have another program here. There's a simple main which has a helper function. So let's look at this one. If we make this main.c, and I'm going to compile it to an O meant to be to an O file. Okay. If we use objdump on that file to look at the machine code, then we find that we have helper and main as machine code, and we have the things we expect. There's a frame pointer set up. When we have a call in main, where does it go to? This call says it goes to 19, but 19 is not helper. In fact, what this call says is just go here, don't go anywhere. What you're seeing is that in an object file, we haven't actually assigned any addresses yet to the helper function main. Whereas if we take this object file and we compile it to a function, an executable, and then look at the executable, and we go back and find main, then we will see that main does have a call to helper. And so at this point is when helper has gotten a particular address so that address can be filled in as in main. So that answers the question of how the compiler knows which addresses to pick in an object file. It doesn't pick the addresses in an object file. It starts out with just assume that everything is at 0, and then when it's going to put those files together, it'll have to assign an address. So how does it know which things to patch up with addresses? The rel-a text section tells us how to do this. So if we look at rel-a text in our main.o, so readelf-a of main.o, look in the file m. Right, there is a rel-a text section, but also readelf knows how to tell us what's in the rel-a text section. It says there is this symbol helper. You need to install its address. You need to install its address at this particular offset in the code. And here's some more information about how to fix it up. In particular, it's a call, and so you need to fix up a 32-bit PC relative address. So it turns out that main and helper main refers to helper through a relative address and a 32-bit with a 32-bit number, because that's always going to be enough to reach the other code. So rel-a text is the information that the object file has to help the linking step know what needs to be fixed up. The symbol table is used by rel-a text. So actually, in the readelf view, it showed the name helper, but actually what readelf does was take a symbol name and actually go look in the symbol table to find out that it's called helper. So when we created main.o, here's a picture of what we got. There was a symbol table that says there are helper and main functions, and the code for those functions reside in the text segment. The text segment, though, currently just has 0 as the place where it's predicted to exist, because that predicted address is not really useful at the object level. And then the rel-a text section, it had a reference to say you need to fix up this part of the machine code in the end so that it refers to wherever helper ends up. And so what the linker does is take that object code, it fixes it up. It gets rid of the rel-a text section because it doesn't need it anymore. The symbol table turns into a dyn-sim table because maybe we need to know where helper and main are for dynamic linking, or maybe it won't be necessary, but in a modern executable, that information is pretty much always there. You can see that the jump address has been patched by the linker. So it now jumps to a specific address. It turns out through a relative reference, but it points specifically to the place where helper exists. So that's how a linker takes object files and turns it into executable files. assigning addresses for the particular things defined in an object file to where they will exist in an execution. Let's look at that for multiple files. Suppose we have a.c, which defines a, b.c, which defines b, and then main, which is going to use a and b. So the answer to the original mystery was the compiler compiles a and b with no particular prediction for where a and b are going to reside. It just says there is a, its implementation is in the text segment. There is a b, its implementation is this text segment. And then for main.o, we have information that says we're going to call a and we're going to call b. Whatever a and b turn out to be, those addresses should be patched. And by the way, this is the main function. And then the symbol table also says there are a and b, but they're not defined here. There's type information in the symbol table says a and b should be provided by other object files when they're linked together. A linker then will take these three object files and it'll put them together into one executable by taking all of the text segments and stacking them together in a single text segment. And as it does that, then it picks addresses for main and for a and for b, and it records that in the dynamic symbol table in case we need it. But more importantly, it also causes the calls that were in the original main object to refer to the new places selected for a and for b.